What?
Is this new thing we're gonna learn?
Yeah. Yeah. I'm not going to really use this PowerPoint, but I'm going to pull it up just for a second here. Okay. Let's talk about points, lines, and planes. I want to talk about some stuff in geometry. Now, this first chapter we do is just very introductory. There's not very much math type stuff that we're dealing with here. A lot of it's just concepts, vocabulary, things like that. And this is so straightforward that I mean, there's not a lot of different examples and math problems I'm going to give you, but I want to challenge you to think about this stuff in a mathematical way, points, lines, and planes. In geometry, and in life too, but especially in geometry and in math, words are really important to us. They have very precise meanings. So a definition uses known words that we already understand to describe new words. Okay, so and that's the way we learn too. You learn new stuff in terms of old things, and that's just to connect this with our little discussion we started yesterday. That is the only way that people learn. People learn by attaching new concepts and meanings to prior knowledge. And to the degree you can always make those attachments, you can make your learning easier. Now, but you got to start somewhere, don't you?
Yeah.
So in geometry, we're going to define things in terms of known words, but at some point you get back to the most basic concepts, and you can't describe those in terms of words other than the words that you're talking about. For example, a point. What's a point? Tip of the arrow, you could say. There's an idea. What else? Somebody throw out some ideas for what is it? Go ahead, Joey. Okay, so we could take an XY plane and make a dot on there, and it's going to have some coordinates, and that's a point. And you're right. In math, that's how we talk about points. Any other ideas on a point?
An intersection of two lines.
Intersection of two lines, a good way to describe a point. Okay, so there's some things we could start to say, but are those really definitions, or are they just examples? Yeah, they're really just examples, aren't they? Turns out that a point, and we're talking about lines and planes also, those are what we call undefined terms in geometry. They're so basic that we can't even really define them. We just know what they are. We can talk about them, and we get a sense that we all recognize it. We all know what we mean, but you can't really define it in terms of other words that are going to give a precise meaning to it. So undefined terms, those happen. Those happen in geometry. Those happen in math. We just have to agree that this is what we mean when we say a point or a line or a plane. Now, what about those things? Let's get a little more specific. So you kind of gave me some ideas about a point. What about a line? How would you describe a line?
A thin, long, straight.
Okay, so I'm hearing thin, long, straight. How long does it go? Forever. Okay, so we're getting some ideas now, right? What about a plane? A plane. You guys know what a plane is?
An area where everything's flat.
Okay, it's like a flat surface. Like here's a plane, right? The whiteboard. Okay, these are good ideas. These are good ideas. So have you guys ever seen a point before? Okay. Have you ever seen a line before?
Yeah.
Have you ever drawn a line before?
Yeah.
Okay. You've seen a plane before?
Yes.
Okay. I'm going to say no. You haven't. You've never seen a point, you've never seen a line, and you've never seen a plane, for sure. It's impossible that you have. You never have. You've never drawn a line, honestly. You never have. And it's not just because it was squiggly. Even if you used a straight edge, you've never drawn a line. You've never drawn a line segment. You really haven't. You know how I know that? Why? Because they don't exist. They're completely abstract and unreal. There's no such thing as a point. There's no such thing as a line. There's no such thing as a plane.
Are you calling us liars?
I guess. I don't know. Now, why? How can I say that? I'm absolutely certain that I'm right when I say that. Why is it, for example, that there's no such thing as a line? How have you never seen a line or drawn a line before? Why? Okay, maybe because a line never ends. There's one good answer. Well, let's restrict it to just a line segment, just a piece of a line. You've never even done that. Now, you might have drawn something that's representative of that concept, but why could you never actually draw a line segment?
Kids we don't know what it is.
Well, okay, I mean, we kind of have an idea what it should be, right? But if we think about describing, let's go back to that description of a line, and let's kind of pick that apart a little bit. They were good ideas. Goes forever, sure. But if people talk about a line as being something that's thin or narrow, that doesn't do it justice. It's not really enough. If I stretch out something like a garden hose, how many dimensions does that garden hose have? It's a three-dimensional object, isn't it? Certainly. It's got, I can see that it goes a long distance in this direction. Let's say we got it stretched across the room here. But it's also got a little bit of thickness this way, and it's got a little bit of thickness this way to it also, right? So it's definitely a three-dimensional object, right? It might look like a line if I get far enough away from it, but it's not, right? It's too thick. Well, is there anything in the world conceivably that could ever represent a line? How thick is a line?
We.
Say it again. Has no thickness. Exactly. So if you ever were to, you could never see a line because it couldn't even be visible, even if it did exist, because it's got no thickness to it. Right? How many dimensions is a line?
None, because it has no.
It's one. It only has one direction in which it's got any kind of thickness or size. It's only got a length along the direction that the line is drawn. So, right, we can't draw, but you know what I'm saying. It doesn't have any thickness this way or this way, so it's strictly a one-dimensional object. But we live in a three-dimensional universe, and so nothing that's one-dimensional can really coexist with our universe. It doesn't work. It can't exist. What about a point? Even worse. How big is a point? How big? Nothing. It has no size at all. It's zero-dimensional. It has nothing measurable about it. There's no size to it conceivably. So a point doesn't exist. It can't exist because it doesn't have any size, right? In our universe, for anything to exist, it has to have size, and so a point can't exist. And even a plane doesn't work. A plane doesn't work because it's probably the easiest to maybe talk about. It seems like I do a lot of drawing on a plane up in the front of the room. Special delivery. But even a plane doesn't work because how thick is a plane, folks? Not at all. A plane, here's an example of a plane. Oh, it went away. Here's a plane. I can draw this direction and I can draw this direction. So it's got lots of measurable distance in those two directions, but it doesn't have any thickness to it. So a plane, we'd say, is two-dimensional. But once again, two-dimensional doesn't work in our three-dimensional universe, right? Now, even some things like talking about, people described a line as being straight. Even the word straight is kind of a loaded term. That's not something that in math is all that meaningful. Let's take, for example, I'm going to give you an example of some straight lines that don't do what you would normally predict them to do. Let's take a globe, a sphere. We'll just think of it as a globe. Okay, so there's our globe. If I draw some straight lines on this globe, and by straight lines, let's just say this. I'm gonna borrow, you know that little wheel doohickey used for cross-country courses that you know what I'm talking about? So I'm gonna borrow a couple of those, and we're gonna go out and we're gonna go to the equator. So we're taking a little field trip to the equator. So we're in Africa. Okay. We're gonna take these things and we're gonna line them up with a laser beam. We're gonna set up these two laser beams that are gonna define these straight lines in the sand in the desert someplace in Africa. And we're gonna start these things going due north, right? Absolutely parallel to each other, straight lines. We can measure it with a laser. When we start these things off, they're exactly parallel. Now, if we don't ever look to the right or the left, but we wheel both of these things north forever towards the North Pole, what's eventually gonna happen to them? Okay, but there's a freak ice storm and the water's all frozen. We can just keep going straight. So right through the Mediterranean, keep going. What do we notice? What's going to happen? They're going to curve with the surface, right? But from our perspective, they still look pretty straight, don't they?
Yeah.
Right? Now they're parallel though. Parallel straight lines, they should never meet, right? Parallel lines is railroad tracks, right? They go forever and never cross, right? Okay. Well, no, that's not gonna happen. Here's the equator. Here are these two places where we started, right? And both of those are traveling due north towards that point. They are gonna cross. They're gonna meet at the North Pole, right? And so you have to even be careful about, when you say words like straight or parallel, things like that, you really have to be careful how you're using those because they don't mean the same thing in different contexts. The geometry that we're doing in here is a pretty simple brand of geometry. We're gonna do almost exclusively what we call plane geometry. We're gonna do the geometry of things that we can draw on a flat surface. But that's not the only kind of geometry out there. There is spherical geometry. There is hyperbolic geometry where you would do geometry like on the surface of a saddle. And that's even weirder. Then parallel lines don't meet, they diverge. And these things, now, why do we talk about these things? Because really the world is, parallel is parallel, right? Not really. The universe, if you look at the universe on a really large scale, it turns out that the geometry, the three-dimensional geometry of the universe is not flat. It has some curvature to it. And I can prove it to you. This is a little bizarre, but this is what's really going on. Now, if I drop this thing, what's going to happen?
It's gonna fall.
It's going to fall. See if you're right. Yeah, it does. It falls. Okay, why does it fall?
Because of gravity.
Because of gravity, of course. Well, what's gravity?
Gravity's the force.
Gravity. Okay, so a massive object pulls on another object. What's the massive object that's pulling on this thing? The Earth, right? And it's actually, where's it falling towards?
The force.
Yeah, it's falling towards the center of the Earth. The ground gets in the way or the table gets in the way, but if it had its way, it'd keep going right down to the center of the Earth. That's right. Okay, so that's telling us why it happens. It's the mass of the Earth that's causing it. That's right. The mass of the tape that's responding to that, but that's not enough. Why is it doing this? You're telling me, yeah, it's due to the mass, but how? How is it happening when I drop that thing?
It's heavy.
What is going on? Seems like a simple question. Can't you give me a good answer for that? Gosh, what's going on? I dropped this thing. What's causing it to fall? What's gravity? You didn't tell me what gravity is. What's gravity?
It's nothing.
Well, it's something. That's falling. I mean, it doesn't just sit there. It definitely moves. When I drop it, what was it again? Pulls you down. Okay, it pulls or pushes. That sounds like a force. Right? Maybe we could call it a force. Does that solve the problem?
No.
Not really. Not really. In fact, we could have had this discussion, if we had this discussion, if we had it about 103 years ago, we would have had to leave the discussion saying, you got me, I don't know. There's no explanation for why this thing, we can describe it. There are physics equations, and that's actually what I studied is physics. I studied math as a part of physics, but my background is physics. And that's where we talk about how the world works, and a big part of that is describing motion in nets. And so there's lots of fancy equations that tell us if I drop something, how long is it going to take to get to the ground? How fast is it going when it's fallen 2 meters? We can describe all that stuff very accurately. But all we're doing is describing. We're not really explaining. We're just describing the motion. We didn't know until about 1908 or so. Yes, cool. We didn't know until about 1908 or so that there's a real reason for this, and it's bizarre beyond belief. Much more bizarre than you would have thought. What's really happening, and I'm telling you the truth here, this is not some kind of hypothetical what if, maybe, maybe not. This has been shown to be true in thousands or tens of thousands of science experiments, physics experiments, with unbelievable accuracy. This is absolutely what's going on. If I drop this tape, it is literally falling into a higher dimensional, call it a 4-dimensional gravity well that's caused a divot in space caused by the mass of the Earth. That's really what's happening. That's what causes the force. I mean, it's pretty bizarre, but that really is what happens. Do you believe me? It sounds pretty strange.
Sounds like
don't just believe me. I guess I'm telling you the truth. But that's the truth. That's the truth. And people at first were very skeptical, as you might be when you hear something bizarre like that. That's Einstein tells us that space is being warped by mass, and that's why gravity exists. If you go far, far away from anything with mass, space gets very flat. And things aren't distorted. They don't, there's no well for them to slide into. But this thing really is sliding into a fourth dimensional gravity well. Here's a little bit here's the proof that made people realize that Einstein really was as smart as he was saying he was, and this really is the way things work. If you look at, there's our sun, and here's Earth revolving around our sun way out here, orbiting about the sun. If we take Mercury, Mercury is a planet that's very close to the sun, right? Closest planet to the sun. Now, it's not very complicated. You could leave high school understanding essentially all of the math required to be able to predict where a satellite is going to be in orbit at a certain time, where the moon is going to be around the Earth, where the Earth is going to be around the sun. And we could run this movie forward for hundreds of thousands of years and very accurately predict, I mean, spectacular accuracy, predict where all of these objects are. It's just easy to do. The math is very, very simple. It works for everything, except it didn't work for Mercury. When scientists looked at Mercury, and they knew exactly how far from the sun it was. It's easy to measure that. When they predicted how long a year should be on Mercury, you know, how long it takes for this thing to orbit around the sun, they were totally off. In the amount of time that all the physics predicted Mercury should have traveled one complete orbit around the sun, it actually traveled a little further than that. It went too far. It was impossible. It's the only case of all the, you know, thousands and thousands and thousands of examples where we looked at this that it was exactly right, the math. Here it was wrong. Why do you think it was wrong? Any ideas why it might have been wrong? What do you think? Yeah, because it was so close to the sun. The sun's big. The sun has a tremendous amount of mass. And so when something gets close to the sun like that, it's going to behave maybe a little differently. That environment is different than all the stuff we're used to. The Earth is small. It's, you know, the mass of the Earth is no big deal. But the mass of the sun is enormous. And so the sun warps the space around it in a much more noticeable way than the Earth does, for example. And so what really was happening here was that the sun was stretching, was creating this divot in space, and it changed the distance around the sun. It actually warped it enough that it did that. Here's a way to think about it. If you took a basketball, so let's say here's a basketball, and if we took like a flat, what would this be? It'd be like have you ever seen those frisbees that have like a wire? They're rubber, and then they've got like a rim around them that the rubber's stretched over. You know what I'm talking about? Or think of it like a drum head or something like that. You know, where you've got a flat circle. Yeah, like a trampoline. There you go, like the surface of a trampoline. Something that's circular but flexible. Now, if I take this thing and I drape it over the surface of a sphere, what happens to it? Okay, now what used to look like this, right? There's the center, and here are maybe the lines that are connecting the rim of this thing to the center. If I stretch that over a sphere, what's it do?
Yeah.
So there's the edge of this thing, but hasn't it been stretched up like this now? Right? And so even though the circumference of this circle is staying the same, what's happening to the radius? How far does an ant have to walk to get from there to there when it's flat compared to when it's stretched over the basketball? Where does he have to walk further to get to the center of this thing? Well, yeah, he has to walk further here, doesn't he? Because he's not just walking in that straight line that we would see, that straight line right to the center. He's walking this stretched distance to that center, right? And so the circumference of this circle doesn't match its radius anymore, and that really happens. So the circumference of Mercury's orbit around the sun did not match its distance from the sun because of the warping of space. It warps it like a sphere like this. And so that's what explained it. And when you used Einstein's equations, and you looked at this previously irreconcilable problem that nobody could figure out, as soon as you started using Einstein's equations, it fit perfectly. It exactly predicted where that would be. Here's another example. These are just easy ones. There's more complicated ones we can talk about. But I think these are kind of interesting. Fiber. Where's fiber? Okay, here's another one. If you look at you can't really look by the sun. If there's a star, stars are all over the sky, but if you want to try to see a star that's right next to the sun, you can't do it very easily because the sun is so bright, so intrinsically bright that, there's too big of a difference in light intensities there, and no matter what you're using. It's just too hard to do. But there's one time when you can do that accurately, and that's during an eclipse, during a solar eclipse. So when the moon perfectly blocks the sun, you can actually look by the edge of the sun and see stars that you couldn't otherwise see. Now we know, and you probably have some sense of this, we know exactly where all the stars are at any time relative to the Earth. As the Earth moves around the sun and spins, we have star charts that would predict for any date you want where every star is going to be with amazing precision. Okay? But something weird happens here. There are some stars, like for example, there's a star that's supposed to be obscured by the sun. It's supposed to be behind the sun. Okay? So we shouldn't be able to see it. But during this solar eclipse, and it's in the right spot until we drift into position where the sun starts to obscure this thing. Then what happens is this thing kind of migrates over here. The star all of a sudden is visible, but once the eclipse has passed and the moon has moved away from the sun, it mysteriously moves right back to where it's supposed to be, to that spot in the sky. Now, do you suppose the star is actually migrating millions of light years through space for our? No, certainly not, right? It's staying in place, but what's going on? Yeah, once again, it has to do with the mass of the sun. And so because the sun is so massive, it's warping space, and it's creating a straight line path that wasn't there before, but when you bend space, all of a sudden there is this straight line path that connects you to that star, even though it ought to be behind the sun. And it really does happen. Every time there's an eclipse, you can see it happen. And that's Einstein's general relativity at work again. So what am I saying with this? What I really want you to understand is just that you got to be careful with these ideas of straight and parallel and lines. And there are some bizarre cases that are real. I mean, they describe the universe that aren't what you'd anticipate. You got to be a little careful with this. This is kind of a bizarre concept. Now we just talked about how there's no such thing as a line, and yet we all know what a line means. There's no such thing as a point, and yet we use these things all the time. In fact, if you want to understand the way the world works, that's what physics does. If you want to know exactly why, for example, if you want to know if I'm going to shoot a bullet at a certain velocity, and I know what the air pressure is, and I know all this, the air temperature is, and all that, we can predict with amazing using physics. You can figure out exactly where that thing's going to land. And so the math is doing an important thing there, right? It's helping us understand the way our world really does work. Because we really did shoot that bullet, and it really did land there, and we really did predict where it was going to land. But we just said that the line and the point and the plane and all these things are totally made up. In fact, you can extend that to all the mathematics. Mathematics, people always ask me, why do we have to know this stuff? What's so important about this? And there's a variety of answers that I really could give you. I mean, we could talk about how important it is to having a good career and getting benefits and all. And there's all kinds of things like that we could talk about. We could talk about how it makes your brain stronger. But here's an answer you won't often hear. I think it's part of the reason we want to know about math is because it is the only thing you ever deal with which is completely abstract and completely made up. There's absolutely nothing real about it. I defy you to find a concept in math that is real. Even things as basic as counting. If I say the number 4, what is that?
It's a number.
Well, it's a number, but you just use the word, you use the number to describe itself. That doesn't work. You could say it's a counting principle. If there were 4 apples sitting on the table, I could point to that and say 4, and we all know what it means. But once again, it's just an abstract counting principle. It's a concept. But even that is not real. Pretty bizarre. Now I'll talk about this more later.
Blowing my mind right now.
I know, it's good, huh?
It's magic.
It's pretty weird. This stuff is, but you never thought about it that way. But I think it gives math a new meaning. I mean, there's something I'm going to tell you right now that if you never knew a reason to like math just for the sake of math, this ought to do it for you. I'm not going to go into details now, but sometime when we have a little bit of a break between topics, I will tell you some more about this. It's really interesting. a lot of the smartest people in the world, you know, they're physicists and cosmologists that are just, I mean, they're huge brains and they think all the time. But one of the things they think about is multiverse theory, you know, about what's the boundary of our universe look like, and there's a lot of actually even observable evidence that helps us understand how that stuff works. And there's an increasing number of these people that are starting to believe that our universe is just one bubble universe in an infinite multiverse. And that conceivably there could be an infinite number of other universes that have just different parameters than ours. Totally different. Could be different number of extended dimensions. I mean, we have 3 extended dimensions, but maybe some of these only have 2 or have 4 or 5. What would that look like? You can't even, we don't know. I mean, you couldn't conceive of it because all we know is 3 dimensions. They might have more than one time dimension. They might have different physical constants where, you know, the atom's force of gravity is slightly stronger, or the strong force acts on a nuclear strong force acts over slightly different distances. You know, the strength versus distance ratio is a little different. That would have profound effects. All this stuff would make bizarre universes. Yes, sir.
Different concepts and just simply different too, like everything is right here.
Well, sure. If there were an infinite number of them, then there'd be an infinite number of them like ours too. But I mean, this is all pretty speculative. But here's the thing that I'm not saying this is the way it is. We don't know. I mean, but this is something people are speculating about. But here's the conclusion they've come to. If you were to take all these infinitely bizarre variation of universes, suppose that in one or more of these universes there are some other weird creatures that are nothing like us. Biology there is totally different, but somehow they're in some kind of bizarre in their world, the geometry class talking about weird stuff, kind of wondering what this guy's talking about.
that all the time.
Okay, but now if they're doing that, maybe they're in a 5-dimensional universe. If they're doing that, here's my question to you. Are they using the same mathematics, or would mathematics be different in their universe?
It would be the same.
How is 5 dimensions?
Well, 5 dimensions, mathematically, it's easy. But it's just not, physically, we only have 3 extended dimensions, although I will tell you
I'm still.
that
Well, am I not able to comprehend what that
no, you can't, nobody can. You can't comprehend what it would look like because it's there. I mean, there's just no way to conceive of it because all your experience and all the visual information you've ever had has pertained to 3 dimensions, and so there's no frame of reference for you or me or anybody to understand what that would look like.
Can I go back?
Yeah. But cosmologists really do think that it's highly likely that our universe doesn't just have 3; it actually has 9 physical dimensions, but 6 of them are just tightly curled up so you can't see them. But so I mean, this dimension thing. It's not as weird as it sounds. Conceivably, it could be that there are some places like this. Not that we could ever get to, but if there were, here's what these physicists all agree on, and this is the part that I think is so profound. Regardless of how much these universes vary from one another and how weird they get, what they all tend to agree on, they're all coming to the same conclusion, is that if they do math in these universes, it's exactly the same as the math that we do. There is only one mathematics which transcends even the universe that we live in. Pretty bizarre. Think about that one for a second. There's nothing else you could say that about. Nothing else would be the same. Nothing physical in these other universes would be the same as ours. You know, we couldn't exist there because we don't have the right number of dimensions. Nothing else would translate. But the one thing that would is that the mathematics would all be the same. Our mathematics right now describes 5 dimensions easily. We have the tools to understand how that universe might work. We just don't know what the physics is, right? We just use the whole comprehensive mathematics to describe our universe, but it could describe others as well. So to me, that's amazing. I mean, so you're really tapping into something when you study mathematics and you start to understand the way mathematics works. It's like a language that just goes beyond country to country. I mean, it literally could go from universe to universe, and it's something real. It's something real in the sense, even though you can't ever see this stuff, it describes any conceivable universe in perfect detail. That's pretty amazing. I mean, why would you not want to understand that more? That's pretty good. And it's, you know, I know it can get pretty boring, and it can get pretty, the way it's presented sometimes turns people off to it, but the mathematics itself is really, seen in that light, is a pretty beautiful thing. I mean, it's totally abstract, but if you understand it, it's the same as the way somebody else understands it at some level. So I don't know. I think that's pretty interesting. Okay, so what about a couple terms here, getting back on track. Yeah, if we get back on track here, I don't know if I can after that, but I'll try. I don't want to do too much of this. I want to just give you some terms. So a point, and tell you how you do this in Moodle. So point has no dimensions. It's usually represented by a small dot. In Moodle, here's how we would write it. We'd write it as point A, the word point, followed by, in parentheses, you would just put the point that we're talking about. Point A, for example. Or even just a capital A. It'll make sense when you get to it. A line extends forever, right? It's one-dimensional, we said. It's represented by, if I want to label this line that passes through points A and B, we just write it as an A and a B, and on the top of it, we put this little line with arrows at both ends. And of course, what do the arrows represent on a line? Why do we put those arrows there?
Forever.
Yeah, because it goes forever. Good. Okay, so, and in Moodle, we'd write it like this. We just write it as a line, and then in parentheses, we put the 2 points that define that line. Okay. Plane extends in 2 dimensions. It's usually we represent it by some kind of like a tabletop shape, but of course it goes forever. The way we write it in Moodle is just the word plane followed by the 3 points. Why 3 points? Well, wouldn't you agree that it only takes 1 point to define a point? How many points does it take to specify a line?
3 and 2.
If I take a single point, let me just draw, let's take this point A right here on the board. How many lines could conceivably go through that point?
2.
More than that. Infinite number, right? 1 point is not enough. But as soon as I draw a second point, B, how many lines could go through those 2 points? No,
2.
only 1. There's only 1 line that can go through 2 points. That specifies a single specific line. How about that? For a plane, it's just 1 extra. For a plane, if I have 2 points, that's not enough. 2 points makes a line. But now if we think in the room here, I want to illustrate this for you. Can you find some examples of things in the room that are like a plane, that might represent a plane? Ceiling. What's another one?
It's a TV screen.
TV screen. How about big stuff? Ceiling, floor, wall, right? Okay, now, let's take 2 of these. Let's take 2 of these. Let's take the ceiling and the floor. We'd say those are parallel planes, and so they never intersect, right? But let's take, how about the ceiling and the rush wall over here, right? Okay, the holy wall. If we take this wall and this ceiling, where do they intersect?
In the middle.
Okay, they intersect at that joint. Looks like a line, doesn't it? Right? So they intersect in a line. How many points are there on that line? Infinite number. So just taking 2 points that define a line is not enough, right? If I take 2 points, I can connect those with a line, and there are an infinite number of planes that could connect on that line. We only see 2 of them here, but couldn't I also imagine another one, for example, that kind of went up at an angle and still hit that line? And I could pick an infinite number of those, couldn't I, right? So all I have to do, though, if I want to specify the wall instead of the ceiling or this other plane, is put a 3rd point up there, right? There it is. Now I've got 2 points on that line and a 3rd point down here off the line. And that specifies the plane, right? There's a pattern there, if you notice that. We said that a point was 0-dimensional. It only takes 1 point to define itself, right? So 0D requires 1, I've done this in a long time, actually written like something other than a smart one. 0-dimensional requires 1 point. We said a line was 1-dimensional, and that requires 2 points, right? We said a plane was 2-dimensional, and that required 3 points. So we could extend that. How many unique points that were not all in the same planes would we have to use to describe a 3-dimensional space, like our universe, for example? 4 points. Yeah, I could take those 2 points that are on the line. There's my 3rd one. Then I could pick another point that's off of that plane, like right here. And that describes a unique volume universe. And only our universe can be described by those 4 points. Now, if I wanted to extend that up to a higher dimension, 4 dimensions would require 5 points. And just like this will blow your mind too. Just like we said that there are an infinite number of planes that could travel through 2 points, there are an infinite number of 4-dimensional spaces that could intersect our 3-dimensional space. How about that one?
Yeah, it's magical.
Okay, so so there's a pattern. Here's some words we have. We could say that if points are all on the same line, we call them collinear. Co means same, right? Points that all lie in the same flat surface in the same plane, we'd call coplanar. So if I wanted to name 3 points that are collinear, what would they be? Looks like maybe D, E, and F are on the same line.
Yeah.
Okay. This is hard to see, but this line is supposed to be coming out of the yellow plane. This one sits in the plane, and this one comes out of the plane. So point H is like outside of the plane. So then D, G, and E, for example, would be coplanar. Okay. All 4 of those, in fact, would be coplanar. And you'll get some practice with this on the homework. It's no big deal. Real quick, another concept we could say that's undefined that we all know what we mean is betweenness. If I have 2 points here, if I want to talk about a point that's on the line that's between those 2 points, it has to be in there somewhere, doesn't it? Right? Okay. Line segment, just a few more definitions. Line segment is just a piece of a line, right? It's got endpoints where it stops. So this one is defined by its 2 endpoints. We call this line segment AB, and we'd write it like this, just with an AB with a line over the top, but now there's no arrows on the line. That means it's a segment and not a line, right? In Moodle, we would just write it like that. The word segment followed by the endpoints in parentheses, AB. What else? Array. Okay, array starts at 1 point, so it does have 1 endpoint, and then it travels through some other point forever, right? So when we write something like ray AB, and this is kind of a big deal, I want you to make sure you understand this. If we write ray AB, that's different from ray BA, isn't it? What's the difference? We call the starting point the terminal point for a ray. So where does this ray start? At A. Where does this one start? At B. Yeah, it's different, isn't it? Okay. We could say that rays that are are opposite like this, like ray CB and ray CA, those are rays that when they get connected together, what do they form?
A line.
A line. Yeah, they form a line. So, does that make sense? That's a good way to think about opposite rays. I don't want to spend too much time on this. I mean, this stuff is pretty self-explanatory. In fact, I think that's probably all I have to do. Yeah, I think we're okay. Yep.
If you're like the smartest person in town,
Oh.
why do you choose to be at high school?
Oh, don't be silly. You know why I like? I'll tell you.